Okay, so Q negative K A, and then what? DH DL. What is H? It's height of what? Yeah, we had a name for it though. It is the height where water sits in our pipe. That's head. And this is the total head. So H is the total head. And what did our total head measure? What was it a measurement of? It's the height of the water column above a given datum. Agreed. What is it? So it's a measurement in length, but why do we care? What is it measuring in the groundwater for us? What sort of, why do we care about the head gradient? It is a measurement of the total energy of the water at that point, right? Head is a measurement of the total energy of the water at that point. So this is total energy. All right. A is the area across which flow is occurring. This can be zoomed out more. Okay. Now, K. K is the hydraulic conductivity. All right, so let's do some unit analysis here. Hydraulic conductivity, let's see. H, what's the unit of H? Length. What's the unit of L? Length. So length over length, this is unitless. What is the unit of area? All right, length squared. What's the unit of Q? Yeah, Q is discharge. Length cubed over time. Okay, great. So what's the unit of hydraulic conductivity? Length over time. All right, so hydraulic conductivity is the ease with which water, key here is water, moves through a media. Hydraulic conductivity is the ease with which water, key, all right, water moves through a rock or a porous media, right? Now, we're going to talk about this double underlined water. So Darcy's law, he measured it and he said, hey, look, it looks like the discharge is linearly related to the head gradient or the gradient in total energy, but across my column, all right? And my fudge factor here is this K, hydraulic gradient. And he was doing the experiment for water, all right? So hydraulic conductivity is specific to water. Now there's all kinds of other fluids that move through media. Air does it, oil and gas do it, helium does it. All kinds of things have to move or can move through porous media. And so we can break hydraulic conductivity up into this expression. So this is little k. I'm going to put a cross through little k as a way to help distinguish little k from big K. Okay? Rho water G over mu. All right, and now let's talk about what these all are. So rho water, we know. What's rho water? Yep, density of water. What is G? Yeah. Okay. Anybody have an idea of what mu might be? Yeah, mu is generally the symbol for viscosity. And here it's the viscosity of water. We'll define viscosity in a second, all right? And little k, this is the biggie, it's called intrinsic permeability. Or oftentimes, for short, it gets called permeability. All right, so hydraulic conductivity has two parts. This first section here, we can think of as properties of the fluid. All right, so here it's water. Now this guy here, this intrinsic permeability is independent of the fluid and is really just a property of the rock. So this is the property of the media. All right, so intrinsic permeability and then properties of the fluid. So this is breaking hydraulic conductivity up into different portions, all right? Now, the reason why we want to do this is if we were interested, for example, in the flow of oil and gas through the rock, then it's this little K, and then we would replace these guys here with properties of oil or gas, all right? So we can calculate oil conductivity quite easily, all right? And it is just using the intrinsic permeability, and then here we would substitute density of water and viscosity of water for the density and viscosity of oil. All right, so hydraulic conductivity. Let's do a unit analysis really quick. So hydraulic conductivity has units of length over time, right? What are the units of density? Mass over volume. Kilogram per meter cubed or something, right? What are the units for acceleration? Length over time squared. Okay, so this is density, we got gravity. Anybody list off the unit of viscosity really quick? It is. Viscosity is ends up having the unit mass
So kilograms meter second.
per length time. Yep. So Mark just said or kilograms meter second. It's mass over length times time. Okay. So these guys cancel out. This, we end up with actually this one, and this cancel out. So we end up with 1 over length. And this cancel out. So we are now, this guy simplifies to 1 over length times time. So what does the units of intrinsic permeability need to be? If I need to make this length per time, and I am right now at 1 over length times time. Yep. All right, so K needs to be length squared. Those two will cancel out, and I'll end up with length per time. So permeability or intrinsic permeability has units of length squared. And this is the measurement, this is the ease with which any fluid moves through the media. So hydraulic conductivity is specific to water. We need to remember that. All right. And intrinsic permeability is the ease with which any fluid moves through the media.
So does that mean that permeability is directly related to area then?
So Mark Reel asked if permeability is directly related to area, and the answer is not really. No, it has like an area unit, but it's not really related to an area per se. Okay, so hydraulic conductivity, the ease with which water can move through a rock is a function of the porous media, all right? The intrinsic permeability, the ease with which any fluid could, and the properties of the fluid, here water, all right? So let's briefly talk about some of these properties of water that control hydraulic conductivity. So let's just hit properties of water really quick. Okay, what's the chemical formula for water? H2O. All right, so we got this oxygen up here. We got two little hydrogens. All right, and they're connected by these bonds. So here's O and H. All right. Now oxygen is greedy, and it keeps the electron nearby. And the hydrogens are happy to give their electron up. So water has a negative and a positive side to the molecule. So it's a polar molecule. And that's going to be important to us for a couple reasons. All right. So first of all, the polar molecule means that other oxygen water will tend to line up in such a way that the positives, line up with the negative end of the other molecule. And that causes an attraction between the water molecules. All right, so because water is polar, the water molecules have an electrostatic attraction. All right, and that's important for us because it controls plays a role in two important properties for us. The first is viscosity. And then the second one that we'll talk about in just a second is capillarity. All right. So viscosity. What's viscosity? Yeah, so we think about it like when I say this fluid has a really well, let's put it this way. When I say this fluid has a low viscosity, what does that mean to you? Yeah, it doesn't move very fast, right? If it has a high viscosity, what does it mean? All right, so let's try and make this a little more formal and say that viscosity is the resistance of the fluid to shear stress. All right. So we can think about viscosity in this way. Let's say I've got two parallel plates. So here's one plate. And I've got another plate up here. All right. And in between this plate, I've got fluid. So this is fluid filled. And I pull on this plate with a force. All right. So this plate and this plate here is fixed. All right. So I've got a fluid in between here and I'm pulling on this plate and I'm exerting a force. What viscosity tells me is how much force do I have to exert to get the fluid moving. So my fluid velocity profile in this experiment would look something like this. It'd be moving at the velocity of the plate right at the top, and then it would be fixed at the bottom. And what viscosity tells me is how much force do I have to apply? How hard do I have to pull this plate to get it moving? All right, to get that fluid moving. And if this plate has an area A, then I can say that the total force that I need to move this plate is the area times the viscosity times the change in velocity, dv, over the change in z. So this is the slope of the velocity profile. The main takeaway here is that viscosity relates amount of force needed to move to make water move. How about I get rid of water there and just say fluid to be more general. All right, so mu relates the amount of force needed to make my fluid move. So it makes sense that it's going to play an important role in figuring out how much head gradient I need to get water moving through the media. Some things that can affect viscosity. What do you think factors affecting viscosity? Yeah, what was that, Finch? temperature. All right, when I want to put honey in my oatmeal in the morning and it's winter time, I got to stick it in the microwave for a while and heat it up before I can get anything to move, right? So temperature is really important. In fact, it's probably the single most important factor controlling the viscosity of a certain fluid. All right. So let me ask you this. If we know that K is equal to little k rho water mu, G, over mu. And this thing's temperature dependent. What does that make hydraulic conductivity? Hydraulic conductivity is temperature dependent. What else would vary with temperature here? Yeah, the density of my water. So hydraulic conductivity is a function of temperature. Now, we're often going to ignore changes in temperature, and we often just report a hydraulic conductivity. We're going to use it, and it doesn't help. You're going to see hydraulic conductivities from tests in Florida in gravels, and you'll say, oh, hydraulic conductivity of gravel looks like it's like 10. Well, if that test was in Florida, the water there's, it could be 20 degrees C. Groundwater up here in Montana is about 4 degrees C. So they're different. We'll make some calculations on how different they are. You'll do it in your homework, but hydraulic conductivity is a function of temperature. We often ignore that change for other reasons, but I want you guys to know that it is a function of temperature. And the hotter the water, the lower the viscosity. What does that do to the temperature or the hydraulic conductivity? So if I make this lower because I increased the temperature, what happens to hydraulic conductivity? It increases. So hot water moves easier through the earth than cold water. Okay, I think this is a reasonable place to take a 5-minute break. And then we'll get into surface tension and capillarity. Okay, so because water has these polar molecules, it likes to stick to itself. All right. And it creates the property of surface tension. All right. So water, it requires a certain amount of force to pull water apart. We have to break those electrostatic attractive bonds. We call those hydrogen bonds. We have to break those in order to pull water apart. So it causes surface tension. So water clings to itself. And that is surface tension. All right, which is basically the force needed to break water apart. to break water. Let's see. How about separate water molecules? I don't want to think like we're breaking the molecule in half because that's an atomic bomb. But these hydrogen bonds, the positive side's attracted to the negative side. It takes some force to pull those puppies apart. All right, and that's the surface tension. All right, so this is sort of property one. And then the other thing is water clings to a charged surface. All right. So if a surface has a polar charge, then the water has a positive or a negative end, and it can flip flop. All right. But as long as that surface has a charge, the water's going to want to hang out next to that surface. All right. And that drives a process called capillarity. Which is essentially the attraction of water to a surface. So let's zoom in on our porous media and let's think about like let's say we're in this porous media and I've got one sand grain here, right? And I've got another sand grain here. And remember that we said that like this big open space was a pore. And this is another pore. And then the tube in between the two pores, do you guys remember what those were called? A pore throat. Okay, so if this pore down here is full of water, what happens is that the water is attracted to the surface of this mineral, because most minerals are charged, have a charged surface. Most silicate minerals have a charged surface. And so the water will be attracted to this surface, all right? And it'll tend to want to climb. As water molecules get attracted, they kind of climb up the side of this tube or the pore throat. All right, so they tend to move up the pore throat. They keep sort of being attracted to the surface. As they do that, as they climb up these pore throats, you know, they've got other bits of water that are attracted to them. And so you end up pulling water up the sides of the pore throat into the pore throat from the pore. All right, and let's say up here, we're right near the water table and this pore up here is full of air. And I'm gonna say for, this is the water table. All right, so an important thing here, look. Capillarity pulls this water up above the water table. That's why the definition of the water table is not where saturation occurs. The definition of the water table is not where all pore throats are saturated. It is the level at which water will rise in a open pipe. It's actually the definition of the water table is where the pressure is equal to atmospheric pressure. We'll get into that a little more later. But what capillarity does is it pulls water up above the water table into these pore throats. All right. Now, surface tension sort of keeps the water together. So it allows these molecules that are climbing up the wall to bring water up inside the tube. So surface tension sort of allows water to fill the tube. And capillarity pulls I'll go over here. Up the surface. All right, if I sort of zoom in here, there's an angle. There's an angle that the water makes with the side of the mineral, this angle here, theta. Theta is called the wetting angle. And it tells me, that angle tells me how attracted water is to this surface. So actually the smaller this angle is, all right, the more attracted water is. It's really trying to climb up this thing hard. So this is an angle. There's X, there's Y. Now, there's an angle here for the air. All right, and it's greater than 90. Right, it goes all the way past my Y and over. So that angle is greater than 90. So whenever we have a fluid that's moving into a pore, there's the wetting fluid, all right? And the wetting fluid has an angle that's less than 90 degrees. And how low that angle is determines how attracted that surface is. So water here is the wetting fluid, all right? There's also a non-wetting fluid, that's here air. So anytime the angle is greater than 90, then you have the non-wetting fluid. So here air we call the non-wetting fluid. These wetting and non-wetting, they become really important when we're thinking about water in the vadose zone. But then also when we have contaminants, oil and gas in our get put into groundwater systems all the time. And now we've got three fluids. We've got oil, we've got water, and we've got air. And depending upon the surface chemistry of the minerals, oil could be the wetting fluid and water can be the non-wetting fluid. So you can have oil trying to pull itself into pores and pushing water out. All right. So the wetting fluid always has an angle of less than 90 degrees. And the smaller the angle, the more important the or the stronger the attraction is between the fluid and the mineral walls. All right, so how far up this tube will water take itself? Well, it'll do it as long as until the surface tension and the wetting angle. The wetting angle is this attraction between wall and water. So the wetting angle is a measure of the force with which water wants to pull itself up, and surface tension is sort of how well it'll keep itself together, and then gravity is pulling down on it. So this height, the height of the capillary rise, which is HC, this height above the water table that the fluid will pull itself into a pore, is a function of the balance of these forces. So it's the surface tension times the cosine of our wetting angle and it's actually 2 times the cosine of the theta because I've got two of these guys pulling up. All right. So I've got gamma is surface tension. It's a force, so it is in newtons per meter. Cosine theta doesn't have a unit. Rho and g have our normal units, but rho g is rho g r, and then r is the radius here. So I should. So theta is our wetting angle. And rho g have the normal definitions, but r is the radius of the tube. Or here, the radius of the pore throat. All right, so if I look at this equation, what are things I can do to increase the height of this capillary rise? Decrease my radius, right? That's basically what I can do. I can not really change the surface tension of water. I have some effect, maybe potentially different minerals might have slightly more affinity to water than others. All right, so I could affect cosine theta a little bit, but mostly it's the radius, the pore throat radius. So this same process is how trees get water hundreds of meters up into, or not hundreds of meters. I guess a really big tree could be 100 meters. All right. Up into the air from the ground. They have tiny little tubes, and it's capillarity. It's capillarity alone, this process that brings water all the way up to the top of the trees. All right, so when we think about, especially when we start talking about water movement in the unsaturated zone above the water table, this these two forces, one is capillarity, which is like tending to pull water up, becomes very important. And it's the pore throat radius that controls how strongly water is pulled into a pore throat. So smaller radius increases my capillary rise. Okay. We're going to talk about some let's see. We're going to talk about saturation, mass wetness, and volumetric water content. And these are other properties of the porous media or ways to describe the porous media, and in particular, the amount of water. So let's say I've got some porous media here. I'm not going to do 3D. All right, and we've talked about the porosity, which is the total volume of the pore space in this porous media. But now we're going to think about this porous media in the case that we're not necessarily fully, all of our pores are not filled with water. So let's say that I've got, portions of this pore space that are full of water. And portions of the pore space that are full of air. So this is air, and this is water. Okay, all saturation, mass wetness, and volumetric water content are ways to describe how much of the pore space is full of water. All right. So the first one we're going to talk about. So first of all, let's recall what's porosity again? Volume of the voids over the total volume. Okay. Now, the first one we're going to talk about, because it's pretty simple, is volumetric water content. All right. Often gets called theta sub W. And it gets defined as the volume of water, the volumetric water, all right, over the total volume. Okay. What is the maximum that this volumetric water, what's the maximum value this volumetric water content could take? Okay, so if all of the volumetric water, if all the volume of the voids is filled, what would be the value of my volumetric water content? So VW here would equal VV, right? So what would it be? What would this go to? Porosity, right? If this is equal to VV, then I have VV over VT, porosity. So this guy varies between 0 and porosity. Its a maximum value is porosity. All right, another one that we use then is saturation, R. And this is the volume of water. So this is, sorry, this is saturation. And it's defined as the volume of water over the volume of the voids. Okay, so what can saturation vary between? Right, so if all my voids are filled with water, then V water is equal to V voids. It goes to 1. So this guy varies between 0 and 1. We can think about this as sort of a normalized volumetric water content, right? All right, one more that we want to define, and that is called mass wetness. We're going to use W here. And mass wetness is the mass of the liquids over the mass of the soil. So the total mass of my porous media. All right, let's this is the we'll just say this. It's when it's dry. So this is just a ratio of the liquid water mass to the mass of the dry sediment. All right, some relationships. That are important. One, my volumetric water content. Recall, I'm taking up too much space. This is equal, the volume of water is equal to the mass of the water divided by the density of the water. The volume total is divided by, it can be defined as the mass of the sediments divided by the dry bulk density, just using the definition of dry bulk density there. And if I do some algebra here, I get MW over MS rho B over rho water. So the mass wetness rho B over rho water. Okay. This relationship is important because, again, it's easy for me to weigh things. I can weigh things wet. I can weigh things dry. I can then calculate the mass of the water by subtracting the dry weight from the wet weight. All right. This is the dry weight. And so this allows me to calculate the volumetric water content just from weighing this thing wet and dry. All right. Another important relationship here. This is one that gets used a lot. Theta sub W equal to VW over VT. And I'm just gonna divide by the volume of the voids here. And I'm gonna multiply by the volume of the voids here. All right. And this guy is the saturation, and this guy is the porosity. So the volumetric water content is equal to the saturation times the porosity. When you read the literature, people often are going to report saturations. If you need the volumetric water content, then you got to know the porosity. And it's easy to convert between the two. All right. So next property we're going to get to here is called specific yield. And this is our first foray into this idea of storage. And we will talk a lot more about storage. But think about storage as basically the water released from a porous media. This is our first intro to it. We're going to talk a lot about storage because there's other forms of storage and there's more specific ways to define it. But for our first intro, just think, well, this is the amount of water I can get out of a porous media. So let's just think about this. Let's start off with a block of porous media and it's fully saturated. So now we know what that means. What does it mean when I say it's has a saturation of 1? Yep, the volume of voids is equal to the volume of water. So all the voids are filled with water. If all the voids are filled with water, what is the volumetric water content? Equal to porosity. So R is equal to 1. Theta sub W is equal to N. Okay, so I drain this puppy. So we let water drain under gravity. So all of our water sort of runs out the bottom here, right? What do you guys think? Now that we know something about capillarity and surface tension, what do you think this porous media looks like after gravity drains? Has all the water left? No, there's still going to be water left in here. Why? What's that? Yeah, it's sticking to the grains. It's been pulled into these pores. So after we drain this puppy, especially the smaller pores, all right, and the pore throats, you know, these smaller pore throats, they're definitely going to still have water in them. So this is the residual water. left after gravity drainage? We're always going to have it in there. It's really, really hard to completely dry out a soil. You got to put it in an oven at 100 degrees and boil it. So now my water content, my volumetric water content is equal to theta sub R. This is called the residual water content. And that is essentially the water content that is left after gravity drainage. Now, what we want to know as groundwater hydrologists is, okay, we went from fully saturated to the residual water content. So we drained this porous media as much as we're going to be able to drain it. And what we want to know is, how many beers does that equal? Right? That's what matters to us. We want to know the volume of the water that was released. All right, and this is, approximately equal to number of beers we can drink out of this water. All right. So that's what we care about. We care about the volume of water released. So what a important property of the porous media for groundwater hydrologists is called the specific yield. And this is actually equal to, this is the volume of water released or drained. All right, this is the volume of water that was able to drain out of this cube. All right, and that's available for us to use. So specific yield is defined as the volume of water that's released under gravity drainage divided by the total volume. Okay. So let's do a quick calculation here. If I have in years past, one of the final projects for this groundwater class has been that I want to start a brewery up Rock Creek. All right. And I want to know how much you guys would have to calculate exactly how much water I'd need per year to make the kind of beer I want to make. And I want to have a garden. So you had to do all this calculations. Now, what I want to know is so the Rock Creek Aquifer is about 10 meters thick. It's about 100 meters wide. All right. And I would have about a kilometer of stream bank. So 1,000 meters. All right. And I'm here to tell you that it is made up of sand and gravel. If I were to completely drain it and there was no other source of water to it, I just totally drained this. How much water? Let's see. And I'm going to give you this. The residual water content is equal to 0.05. And porosity for a sand and gravel is what?
About 3 or 3.5.
0.3. All right. Calculate how much water is available.